All right, so today I will tell you about causal models. And so what are these? So imagine that you have some observed random variables. So it could be, in this example, we have a disease diagnosis graph where we have some diseases, some symptoms, also behavioral or environmental factors, and you try to say what causes what. So what behavior causes what disease causes what symptom, and so on. And so if you ask 1,000 people about all of these different variables, then you have this data, and then you try to learn the graph. So you try to learn what causes what in that situation. Another example is gene regulatory networks, where you have different genes, and you want to say how the expression of a given gene changes the expressions of other genes. And so in general, the question that we're interested in is how can we learn the structure of these graphs? These are directed graphs from observations. And what I mean from observations, I mean, obviously we observe things, but it means without interventions. So usually in causal inference, there's some kind of intervention. For example, when you test whether the vaccine for COVID works, you do a randomized control trial where you randomly give the vaccine or a placebo to people to eliminate other possible reasons that you might or might not get COVID. But here, sometimes it's not ethical or possible to do randomized control trials. Like if you want to see whether COVID causes certain non-COVID things, you can't just force people to get COVID to check if they will get something else afterwards. Okay, so and in these situations, we just have observations. So this is what we mean. There's no interventions, and then we still want to learn the graph. And of course, sometimes you can't quite learn the graph, and you can learn something, maybe some more general object, and I will talk about this soon. All right, and so let me set up the mathematical framework that we will use. So again, we have several random variables, let's say x1 through x5 here, and they are placed, we think of them at the vertices of some directed graph. And then there's directed edges and a structural causal model, or sometimes called a structural equation model, expresses each variable as a function of its causes and some noise. So for example, x1, or the variable vertex 1, has no so the causes are the parents, so the edges pointing to it. So there's no edges pointing to 1, so it's just some function of noise. X2 is a function of noise, so 2 has no parents. 3 has one parent, which is 2. So x3 is a function of x3 and epsilon 3, and so on. So we have all of these. So x5 is a function of x1 and x4, and some noise epsilon 5. And the important thing is that the noise terms, they're independent. Okay, so the whole relationship between the variables comes from this graph, and these noise are just independent. Okay, and in general, the definition is of a structural equation model or structural causal model is that it consists of a directed acyclic graph. So here we'll start without cycles. There's no directed cycles. And I call this a DAG, and this will appear in many slides. So DAG means a directed acyclic graph with vertices V and edges E. We have one random variable xv at each vertex, and then we have equations or assignments that say variable xv is some function fv of its parents and the noise. Okay, and again, the parents are all vertices that point directly to the node v, and then epsilon v is the noise, and these are independent noise terms. All right. And so given samples from such a model, so imagine that you somehow get samples from this model. So these x1 up through xn are vectors lying in R to the v that come from this model. Can we identify the graph G? So just like before, if you ask 1,000 people about their behavior and symptoms, then can you tell what causes what? Okay, and so in general, so if you assume nothing about the model, you cannot learn the graph precisely. So you can't tell if 1 causes 2 or 2 causes 1 in general. So if you have 2 variables, you can just say if they're correlated, but you can't say which way the causality is. And this also happens for Gaussian variables. So if your vector x is a multivariate Gaussian vector, then you still can't quite learn the graph. and also in the discrete case. So if each of the xi's takes finitely many values, there's something called Markov equivalence, which I will explain in another slide. But there are certain models for which you can actually say what the graph is. And this is why they're very interesting, because you can actually tell the precise causal picture without intervention, so just from observational data. And so one is, for example, there's more, but nonlinear models where each fi is nonlinear, but then the noise is additive. So here you would have plus the noise, so plus epsilon 4 plus. So the noise term is just added, but then the function that each variable is of its parents is nonlinear in some way. Okay, and the other case, sorry, it's covered in this, where you can tell, identify the graph is this linear non-Gaussian models, and I will talk about these today. Okay, but before I do that, I wanted to tell you what this Markov equivalence is. So what can you tell, what graphs can you distinguish from observational data in general? Okay, so we call two graphs Markov equivalent, so G and H are Markov equivalent, if they encode the same conditional independent statements. So I'm not going to say what these are, but from the graph, you can tell if a distribution lies, so I haven't defined most of these things, but if a distribution somehow corresponds to a given graph, there are certain conditional independent statements that should hold for this distribution. And they come from a graphical criterion called d-separation, which I'm also not defining, but I will give an example. Okay, and these are precisely the, so usually if you have no assumptions, you can just tell what are the conditional independent statements that hold for this distribution. That's usually what people do. They sort of they learn conditional independent statements, and then they try to learn the graph. And so two graphs are Markov equivalent if they cannot be distinguished. And there's a very nice characterization for precisely when that is. So two graphs, DAGs, the cyclic G and H, on the same vertex set are Markov equivalent, so they cannot be distinguished if and only if they have the same skeleton, meaning that if you remove directions, they have the same underlying undirected graph and the same what is called unshielded colliders. So these are triples of vertices where two point to the other. And these are sometimes called immoralities because there's two parents that are not married. They have a child of this. And so here are these four graphs. They have the same skeleton. So it's just 1, 2, 2, 3, but there's 4 ways to orient the two edges. And these 3 are Markov equivalent. And then this one is on its own. So these form a Markov equivalence class, and this one also forms one. Okay, and there's a conditional independent statement here, which is 1 is independent of 3 given 2. So basically, if you have 2 children, 1 and 3, if you condition on the parent, then they're independent. Whereas, and then there's also these kind of paths, the left and the right. And then the final one, where 1 and 3 are pointing to 2, they're not independent if you condition on 2, but they're actually independent without conditioning on anything. So you have 2 parents, 1 and 3, they're independent, and 3 is their, 2 is their child. And so you don't want, they're independent, but then if you condition on the child, they're no longer independent. Because if you have a child and one parent, you can learn about the other parent. Okay, so this was just a Markov equivalence. It's kind of an interesting combinatorial criterion on the graphs. And the point is that there are certain cases where you can make some assumptions on the model that will give you the ability to actually learn the graph. So to identify the graph. Okay, so today I'll talk about linear models, so linear structural equation models, or causal models, linear causal models. And so here the functions fi, they're all linear. So every vertex, every variable is a linear combination of its causes and the noise. And so this is our example that we have before everything is linear. And in the general case, xi is a linear combination of its parents. So j is a parent of I plus epsilon j. Sorry, I can't see that. Yes. No, epsilon I, of course. Yes, so this is our general definition. And we can rewrite this in matrix vector form. So if x is the whole vector, then x will be equal to lambda transpose x where lambda is this matrix here. So these are its entries. And the matrix lambda encodes the graph. So lambda ij will be 0 if there's no edge from I to j. So basically, if you learn the matrix lambda, then you know the graph. Okay, and plus the vector epsilon. So if you move this part to the left, then we have that x minus lambda transpose x is epsilon, and then multiply by I minus lambda inverse transpose, you get that x is I minus lambda inverse transpose times epsilon. Okay, so our random vector is actually a linear transformation of a vector which has independent entries. And this linear transformation encodes the graph. And so again, here it is. So we have this equation. And now we'll see why we want to think about non-Gaussian vectors. So there's a field called independent component analysis, where they study the following problem. So given that you have a random vector x, which is matrix A times epsilon, and epsilon is a vector of independent components, and you want to recover A. So this is exactly the same. And of course, you can only hope to recover A up to permutation of its columns, because if you permute some columns, then you're permuting the entries of the vector epsilon. And so that's, you can't really learn that. And then you can also scale the columns. If you scale a column, you're scaling the corresponding entry in epsilon. So you can learn A up to permutation and scaling of its columns. And thing is that if at least two of these epsilons are Gaussian, then you can't recover A uniquely. And this just comes from the observation that if you have two independent Gaussian variables, and there exist infinitely many linear combinations that will keep them independent. So because for Gaussian, so if you have two variables, then their covariance matrix is just a 2x2 covariance matrix, right? And it's diagonal if they're independent. Let's say it's the identity for simplicity. So if you apply any orthogonal transformation to the random vector, let's say u, then what you do to the covariance is you do u on one side and u transpose on the other. And so it remains the identity. And so they're still independent. I will show this again in a little bit. And so basically Gaussian's sort of problematic because of this. And if at most one or all of them are non-Gaussian, then you can actually learn A up to permutation and scaling of the columns. So somehow being non-Gaussian here helps and allows you to learn this transformation uniquely. And there's a variety of ways to learn this matrix A. And so this was realized in 2006 by Shimizu et al. That if we now go back to our causal inference problem, you can actually use ICA, independent component analysis, to learn the graph. So basically, you recover this matrix here, and then you can actually find the exact permutation and scalings of the columns, and you can actually recover the matrix lambda, and so you can recover the graph. And so they realized this in 2006, and ever since then there have been many papers on the topic. In fact, Shimizu actually has a book about this subject, and people have tried many different methods, and one of the most successful ones and recent ones is this one, where they actually exploit. They don't use ICA. So ICA has some issues with convergence. It's kind of sometimes a non-convex optimization problem that you have to solve, and there have been many other methods to learn. Basically, this original paper really showed that you can do it, which is the cool part, that you can actually find the graph. And then I want to talk about this algorithm where they use second and higher order moments of the random vector to identify the graph. And so here is an example. We have our two graphs, one causes 2 and 2 causes 1, and these would generally be indistinguishable. But if you are sufficiently non-Gaussian, which I'll explain how, then you can. So consider this equation. So I'm assuming that my random variables x1 and x2 have mean 0. And so these are sort of their covariances. These are the second moments, what I call the covariance matrix. So this is the 1,2 entry of the covariant matrix, the 1,1 entry of the covariant. It's the third moment. Okay, and so this equation that involves the second moments and the third moments. This is the expectation of x1 cubed, and here you have x1 squared and x2. So these are third order moments. This one is 0 in this case, and it's non-zero in this case. So you can actually tell which one it is, and it's non-zero generically. In particular, you need to be sufficiently non-Gaussian because for Gaussian one, these third moments, they'll be 0. So you have to be non-Gaussian enough that the third moments are useful. And you can also use higher moments. They don't have to be third. You can use fourth moments instead of third. This is just an example. Sorry. Okay, and so they have this very nice algorithm where they basically, this equation will hold if one is a source node of the graph, and they just identify source nodes and sequentially kind of remove them from the system, and then they slowly learn the whole graph. And so this is what the algorithm does. It just uses this kind of equation. It's just a quadratic equation with 2 entries. And in fact, this equation is, you can think of it as a determinant, which I'll show in a bit. And this is one of the best algorithms right now, so it's kind of a success story for these algebraic equations. Okay, and so before I go on, so today I'll talk about basically learning these models for graphs that are not necessarily acyclic or that have hidden variables. Okay, so I will talk about hidden variables and cycles, but before I go on, I want to say a little bit more about these equations. If you go back to our equation for the model, we have this. So then we can think about the model as the set of sort of second and third order moments that arise from a given graph. So for a given graph, I want this n2,3 of G to be the set of all possible pairs of covariance matrix and third order moment that could come from this graph. So what I mean by this, so this is m2,3 of G. So first I have S, which is the covariance matrix. And because X is I minus lambda inverse transpose epsilon, then the covariance of X will be I minus lambda inverse transpose times the covariance of epsilon times I minus lambda inverse. It's just by linearity. And this omega2, the covariance of epsilon, is diagonal. So our covariance factorizes, you know, we have a diagonal and then these two on the sides. So it has lambda in it. And if you're only looking at Gaussian models, so here in the non-Gaussian case, but in the Gaussian case, which has been studied a lot, you just have this covariance matrix S. You don't have any higher moments because they don't tell you anything. And so you can learn the Markov equivalence class from this matrix S. And now the thing is that with the non-Gaussian, you actually have the third moment, T, which is meaningful. And this is going to be, okay, so I have this notation here, but basically you take the third moment of epsilon and you apply this linear transformation along. So it's a tensor, it's an n by n by n tensor. And you apply this linear transformation along all 3 of its sides. So you take a cube and you multiply linearly with these matrices. And so your model now is basically all pairs S and T that have this factorization. And again, lambda here has to have a 0 pattern corresponding to the graph. So this is the model. And you know, just as we saw in the previous slide, depending on what the graph is, there will be some relationships among the entries of S and T. Okay, and so we just decided to study what are all of the relationships among S and T. So in fact, in the case where we have a Gaussian vector and we just have S, this has been the topic of study of the field of algebraic statistics, which I'm a part of for a long time, and it's still not completely resolved for graphs that have hidden variables or cyclic graphs. So we just did the first such study where you have now second and third order moments, and we showed that if the graph is, I have a tree DAG here, so it's called a poly tree. So if the skeleton is a tree, the underlying undirected graph is a tree, then all of the equations defining the model. So this model is the image of a polynomial map. And so it's actually an algebraic variety. So it's cut out by polynomial equations. And so all of the equations are actually either just some entries being 0, or so the s's here are the entries of s, and the little t's are the entries of t, or there's some 2 by 2 determinants that are 0. So this matrix, wherever it comes from, it has to have rank 1. Okay, but excuse me. Yeah, so you don't need to see the details, but what I want to say is that you can try to find all of the relationships and perhaps use them in an algorithm for learning the graph. Okay, and of course, you could try to do this for general graphs. As I said, this was just done for graphs whose skeleton is a tree. And we're currently trying to find it for general directed acyclic graphs. And it looks like all of the equations are determinants, which is quite kind of a beautiful combinatorial structure, because you just have some s's and t's, and then the determinants of those can tell you what the graph is. Okay, so now let me tell you what the story is when you have hidden variables. Okay, so now suppose we have the same example from before, where we have these linear equations, but then imagine that variable 1 is hidden, so we don't see it. Okay, and so what happens then is that we have everything the same, but then these terms where we had x1, they go into the noise. And so we get these two noise terms. And now, again, epsilon 2 and epsilon 3 are independent. They're also independent of epsilon 4 and epsilon 5, but epsilon 4 and epsilon 5 are dependent to each other. And we encode this with this bidirected edge. So it's kind of pointing as two arrows to 4 and 5, and the graph has vertices v, directed edges e, and bidirected edges b. This is a very common way to denote the situation. But we'll also study situations where the hidden variable has more children, not just more than 2 children. So if you have this model and we don't observe variable 1, then we can denote it, the graph, like this with a multi-directed edge. Okay, so it's a 3-directed edge where now x2, x3, and x4, they're just noise, but these noise terms they're dependent, and still x5 has its noise term, but it's independent of the other noise terms. Okay, but you can have this kind of graph and have it, yeah. So we call the graph G that has vertices V, edges E, and multi-directed edges H. I think it's H for stands for hyperedge. Okay, and so we would like to learn this graph. And all right, so there's existing methods, and you can still learn this using ICA, independent component analysis. But again, you don't really have guaranteed convergence to global optimum. Or other existing methods, they're good, but they only learned graphs that have only directed and bidirected edges. And so we just improve these by sort of learning a graph that has directed and multi-directed edges. So for example, we can distinguish these two cases, right? So these existing methods either they can learn this kind of case, but they don't have a guaranteed, they don't necessarily converge, or they only learn this case. So what we did was we used some very simple algebraic constraints to improve this case to this case. Okay, and I'll just try to explain this very simply about how we do this. So, all right, so we use cumulants, and cumulants, maybe you know what they are, maybe you don't, but they're just some function of the moments. So the moments of my random vector are just these expectations, and the cumulants are some kind of, they depend on what. You can define them for the moment. So for each number k, the kth cumulant of a random vector is a d by, so our random vector now has d entries. Sorry, it moved from n to d. It's a d by d by d k times, table or tensor, whose entries can be obtained from the moment of x. So for example, for the 4th cumulant, the I1, I2, I3, I4 entry is just this formula using the moments. Okay, and the point is that we can say exactly when accumulant entry vanishes. So now if you have a linear acyclic model with this now graph that has these multi-directed edges, and X has these cumulants CK, then CK at this entry is 0 if and only if these vertices have no common ancestor. So here's my vertices. There could be repeats as well. I1, I try upper IK could be repeated. These are the cases where they do have a common ancestor. So either it's a vertex or maybe it's a hidden variable that's a common ancestor. But if this does not exist, then this entry is 0. Okay, and in particular, this allows us to tell when this happens or this happens, because in this case, they don't have a common ancestor. 2, 3, and 4 do not have a common ancestor, so the cumulant will be 0. But in this case, they do, so it's not 0. And so using this result with some excellent students, undergraduate students from UBC, during RU, we wrote an algorithm where we use existing methods to learn the graph that has bidirected edges like this, and then we use our very simple criterion to improve it to have multi-directed edges. Okay, and so this paper here also characterizes when hyperdeterminants of the cumulant tensor vanish. There's some interesting combinatorial constraints, and it kind of generalizes a very important result for Gaussian, where you have look at determinants of the covariance matrix. Now we look at hyperdeterminants of these tensors. But anyways, I'm happy to talk about this offline. Okay, so this was the case for hidden variables. So now we can use moments, cumulants to learn these graphs with hyper edges. Okay, and so for the rest of the talk, I would like to talk about the cyclic case, meaning what happens if there are directed cycles in the graph. I mean, in reality, there's a lot of systems in which there's these feedback loops, right? So something causes something else, which goes back to the original thing. And so assuming acyclicity is really helpful in theory. I mean, really helpful for designing algorithms, but it might not be realistic. So for example, gene regulatory networks, there's probably definitely cycles, and so on. So the same questions as before. Can we still uniquely learn the graph? So we don't know if we can, because those results were just for DAGs, acyclic graphs. And what algorithms can we use? And this is joint work with my co-authors and still to be written. Okay, and so our first result is that you actually can't quite learn the graph uniquely. It's very simple. So if you have, for example, this cyclic graph, and this is the model, right? So xi is something times its parent plus noise. You can just rewrite the equations. Put this part on the left, divide by lambda for 1. Let me get this. And so you get this model, which corresponds to this cyclic graph. So going the other way. So you have the graph going this way is equivalent to going the other way, because these noise terms are still independent. So it's really also part of a structural causal model with this graph. So you can't quite learn the graph, but you can reverse cycles. And we showed that this is precisely when two graphs are equivalent, meaning they cannot be distinguished in this linear non-Gaussian setting. So this is when, this is complicated, but here's an example. But if and only if you can find some cycles in one graph and reverse them. So let's say, and they have to be disjoint. You have vertex disjoint cycles. So let's say here I have 3, 4, 5. I'm going to reverse it to be 4, 3, 5, and I have to change something. So if I have a vertex that was pointing to 4 before, it has to point now to the parent of 4. So so now 2 points to 3 instead. So I reverse the cycle, and every time you have a vertex, you have an edge vi to vj, where vj was in the cycle. So this was this one. I have to make vi points to vj minus 1, so the parent of vj in the cycle. And there is a name for this, actually. It's called a p adjacency. So in this graphical models literature, so it's a name for when so I'm preserving p adjacencies, something like that. But anyway, so this is still defined, so we know exactly what the equivalence classes are. And another thing to note is that you really, if you have a cycle, you kind of want the product of these constants here on the edges, the lambdas on the edges, you want their product to be less than 1, because things will kind of compound and go out of control. And so it's nice that you can reverse a cycle, because that means that the product now becomes 1 over the original product. So you can really only one element of the equivalence class is kind of feasible, because you want the product to be less than 1. So this allows you to do it. And the existing algorithms, they just kind of chose something where the product is less than 1, but they didn't really know what the equivalence class was. Okay, and so now how can we learn the graph? Again, there's ICA-based algorithms precisely doing this. And we would like to design an algorithm using the higher moments. Okay, and so how do we think about cyclic graphs? So a cyclic graph can be split into these parts called the strong components, where a strong component is just a set of vertices where there's a directed path from every vertex to every other one, and backwards, right? So it's like a big cycle. And so I think of a cyclic graph as a DAG of cycles. So it's like a cyclic graph where the nodes are these big cycles. So here I have these 3 strong components, and then this one, and this one. And so there's an ordering, it's called a topological ordering of these components, meaning a topological ordering in this causal inference literature is basically order your vertices, or in this case, components, so that there's the direction goes upwards. So there's no edge going backwards in the order. All the edges go this way. So for example, here, so you can go from 1, 2, 3, 4 to 9, 10, 11, and then you can also go to 5, 6, 7, 8. So this is the topological ordering. And so the algorithm is going to first find this topological ordering, and then find the edges inside the cycles, and then the edges in between the cycles. Okay, so this is how we can sort of split the problem into different parts. Okay, and our current algorithm will only work for a specific subfamily of cyclic graphs, very simple family. And so we require that these strong components, they're simple cycles. Okay, so here's 1, 2, 3, 4, it's just the cycle 1, 2, 3, 4. Here 9, 10, 11 is just the edges 9 to 10 to 11, 5, 6, 7, and 8. So here there's no edge from 1 to 3, or from 2 to 4, or maybe backwards from 2 to 1. It's just the cycle. So all the strong components are just simple cycles. All right, and this includes the case of directed acyclic graphs, in which case the strong components are just vertices. So it's just one vertex. Okay, and it is easy to describe the equivalence class to such a graph, because you just have to kind of reverse one of these cycles. One of the components, you reverse it, and then change some of the incoming arrows according to that law, and you get the equivalence class. So it's really, you can reverse one of the however many strong components you have, or sorry, one or more of these components. Okay, so and now I'll just show you how we do it, and I'll skip some details, but the point is that we use only relationships in the second and third order moments, and there are sort of low degree polynomials in these second and third order moments, regardless of how large the graph is and the cycles. It doesn't matter how big the cycles are. Okay, so here is an example of this kind of graph whose strong components are just simple cycles. Okay, and so we're going to use certain determinants of our whose entries are second and third moments. So the little s's are entries of the covariance matrix S, the little t's are entries of the complement T. So these are 2 by 2 determinants and 3 by 3 determinants. And so the algorithm in the acyclic case that I described from Wang and Durden, they just use this kind of matrix. So this is exactly what they do. But now, because we have cycles, we're going to use this matrix as well. So we're going to use these two types of matrices. And so first we're going to compute these duv2 and duv3 for every pair of vertices u and v. Okay, and then we're going to first check if there are any root nodes. So root nodes are basically strong components that are sources. So there's nothing pointing to them. And these would be precisely the vertices R for which drv2 and drv3 are all 0. Okay, so in our case, we have 1, and we can remove it. So how do we remove it? So we can, because we have a linear system, we can regress, do linear regression of all the other vertices onto that vertex 1 and take regression residuals. And when you can do this with the data too. So you can sort of have it that your data vectors now are just the residuals and they arise, and you can prove that the new data will arise from this model. So you can prove that if you start off with a random vector that came from this model and you regress on vertex 1, then the residuals arise from this model. Okay, so this is what you do. And then there's another condition that, okay, so you do this a few times because now there could be more root nodes, right? So if you had just a DAG, you're just going to keep having root nodes until you have nothing. Okay, and so now after step 2 doesn't apply anymore. Okay, sorry. Yes, step 1. You go back to step 1. You recompute these guys, these determinants, and then you check again for root nodes. If there is none, then you're going to go to step 4, where we now find all sets of vertices for which the 3×3 determinant vanishes, but a 2×2 doesn't for all vectors, for all u and v. And this set will contain our root cycles, so root strong components that are roots. Okay, and we have a way to find exactly which ones are root cycles, which I'm kind of not skipping some details, but you can do this, and then you can again regress everything else on this cycle. And now you have this model left, and you can repeat these steps. So now we can identify our root nodes, and now we just have 2 root cycles. We identify them, and then we're done. Okay, so what we did is we learned the strong components, right? So we learned the topological ordering. We learned what comes before what. So we had like 1, 2, 3, 4, if you remember the graph. We have this topological ordering, and now we would like to learn ancestry relationships among these cycles. Okay, so what we do is we can do linear regression of the last one on everything before it, and you're just going to get non-zero coefficients from the cycles that are actual parents. So you can prove this. So we get this kind of graph that shows which cycle points to which other cycle. Okay, so I first regress this 8, 9, 10 and everything else, and I see that only 12 points to it. So the only non-zero coefficient is from 12. And then I regress 12 on everything else. Oh, sorry, no, it's 5, 6, 7 on everything else. And then 12, I'm going backwards in this topological order. Then I regress 12 on these guys. And then I see that only 2, 3, 4 points to 12. So anyways, you can learn this. And now the last part is learning the precise edges between these cycles and the actual edges on the cycles and the weights, the lambda weights, which I'm sort of skipping these details, but basically to learn the skeleton of each cycle. So my example, they're just 3 cycles. So in a 3 cycle, it either goes this way or this way. So it's not very complicated. And because for us, we have this set of graphs where you just have simple cycles, you can actually just choose one direction or the other, because as we saw, they're equivalent. So you can just choose the direction. And then, so this, if the graph had more, if the cycle had more than 3 vertices, it was 4 or more, you can actually check exactly what the cycle is using conditional independence, which are algebraic constraints on the covariance matrix. So this we can check. I'm happy to explain this if people are interested to know how. And then we, for each cycle, we want to discover the weights on the cycle. And this is, again, so for a given cycle, no matter how big it is, the weights will satisfy some degree 3 polynomial relationships. So you can actually express the cycle as like the weight on each cycle. So for example, this weight here on this edge 8 to 9 is some ratio of a polynomial of degree 3 divided by another polynomial of degree 3. Okay. And finally, to learn the edges and their weights between the cycles, we do some linear regression. Okay, so I'm sort of omitting the details, but we can, from the top down, learn all of the edges and their weights. Okay, so this is the algorithm, and you know, if you want to know the details, I'm happy to share. But the point is that we just use some degree 3 polynomials and some linear regression. Okay, so so this was sort of the math of my talk, and I just want to say some concluding remarks for this talk. So first of all, we discussed linear non-Gaussian causal models, and we saw that these are interesting because you can actually uniquely learn the graph, unlike other causal models, from observational data. And we saw that this can be learned using second and higher moments in a nice way. And we discussed the cases when there's hidden variables and cycles in the graph. And so what are some future questions that we're interested in working on? Okay, so our algorithm only worked for a specific family of cyclic graphs. So we would like to extend it to all cyclic graphs. And this might be hard, I don't know. So we need some other magical constraints that fold among the moments that will reveal some structure. So what are there more constraints that can be used? We would like to prove that our, that our procedure is consistent, and maybe see how many samples we need, or give some kind of asymptotic rate. And as I said, we're also interested in finding all algebraic constraints for DAG models, or for cyclic models, or for models with hidden variables. So these are questions that people have been asking for a long time in my community for the Gaussian case, where you just have the covariance matrix, but now we have this third order moment tensor, or maybe higher order moments, so fourth and so on, which we haven't even explored, that give more information. And the constraints, at least the ones that we've computed, are always determinants. So they're very beautiful polynomial equations. So they're just saying, oh, this matrix has low rank, so all of its determinants of size, all of its minors of whatever size are 0. It's kind of a very nice combinatorial story. And some other current or recent projects that we are working on are algorithms for learning the graph if you're in the general setting. So if there's no linearity, no Gaussianity, nothing assumed, and you have cycles, can you learn the model? I.e., you have to learn the equivalence class, and it's a very complicated description of the equivalence class for cyclic graphs that I didn't say. And also, I've sort of been working on causal inference for a few years, and every time I talk to someone applied, they say, oh, okay, I have my data, and it's actually time series. So it's not IID samples that I described, like from this clinical trials where you ask 1,000 people to tell you something, but it's actually just, from climate science, they have observations every 30 minutes of the same variable, so they are not independent, they're very, very related. And so, so we're now looking at causal models from dynamical systems, and also looking at gene regulatory networks from gene expression data, which are also sort of time dependent. So they're also not IID there. So they're time dependent, and they're more complicated than these time series because you don't actually have a time series. Yeah, so this is sort of what I'm currently excited about. All right, and that's it. Thank you.
Okay, thank you very much. Are there any questions? Yes. Oh, wait.
Yeah, you are talking of some algebraic conditions that are something that vanish, but you are having random variables. So probably you make some statistical test to decide if it's 0 or not 0. Or...
Yeah, that's a great question. So Yeah, so in algebraic statistics, we always find these polynomial equations and we say, okay, maybe we can test if, if our data comes from this graph or from this graph, but how do you really test when is something zero? And recently there is a paper that actually explains how one should test, how you should design your test statistic for polynomial equations. So they have some procedure using U statistics. Yeah, so there is a way to do it, but yeah, but you have a point. Yes, you can't tell when something is zero.
No, it's for the whole online.
Thank you very much for this great talk. I'm just wondering if you could discuss what it implies to tackle cyclic versus acyclic graph. Because here you have some cycle that you go through, so it seems not to assume temporality, or I'm not sure how it impacts your assumption of temporality, because typically you could change things in time as well if you didn't have. Yeah, so sometimes maybe your samples come from sort of an equilibrium state of a system where there's a cycle. Yeah, because otherwise there is the time component, like this came before this, but maybe you're at equilibrium and you have the samples from this kind of equilibrium distribution, something like this. With a stochastic process, you can do this with something stochastic, or you you would need to have varying, so if you have I'm not sure if that's the question, but if you have time series, then you actually have a lot more information about causality, because one thing comes before the other. So there you can actually identify the graph uniquely under very weak conditions. So I think one condition is, so it doesn't matter if it has cycles, if there's no instantaneous effects. So if instantaneous effect means like something causes something else like immediately, it has to cause it like in time more than zero, something like this. If there's no such effects, I think you can identify the graph even if it has cycles. So I'm not sure if that was your question. Oh, yeah, thank you.
Okay, thank you very much. Other questions? Maybe there are some questions online. I don't see, but we could hear them. Oh yeah, sorry, yes.
I thought you. No. I'm just curious to know how at the end, like one of the open questions is sample complexity. Like how would a sample complexity bound look like? Like, is there any conjecture? Like, how do you expect to be like something on, like, I guess you're going to have a lower bound. What's going to be on the right side of the lower bound?
Yeah, so in this one, so here they have some kind of bound which says how far do the moments have to be from the true, like the actual population moments, in order for you to recover the true graph. So just for the graph structure, and then yeah, so this would be one way for it to look, but I don't think it's done here in this hidden variable case, and we in our cyclic one we haven't thought about it yet, but yeah, so I think the only one I know of is here in this paper. Yeah, so they just say, yeah.
Okay, thanks a lot. I think there are no questions online from what I see, but thanks a lot. Congratulations for the prize, and everyone is invited to a reception next door. So that's it. Thanks.